Guys, welcome back to chapter 12. In this video, we're going to do just a quick plug and chug problem using our new equation for Gibbs free energy. So here's the problem. We want to calculate Gibbs free energy at 25 degrees Celsius for the following reaction. Given is the standard enthalpy and the standard entropy for this reaction. So again, remember this little degree symbol is just telling us that we're dealing with standards. So we're pulling these numbers off of the periodic table. Off of a table, not the periodic. And we're at standard conditions, so 25 degrees Celsius, 1 atm, yada, yada. Okay. So the equation to calculate Gibbs free energy is as follows. The change in Gibbs free energy is going to be equal to the change in enthalpy minus temperature times the change in entropy. Okay. While it seems like a really easy, super straightforward problem, there are some little teeny tiny intricacies that we need to keep an eye on. Okay. So first, let's go ahead and start plugging our values into this equation. So the first thing I'm going to plug in is the entropy change. So that is a positive 95.7 kilojoules minus temperature. Now it gives us temperature in Celsius. But if we peek down here at the units for entropy, what is that unit on the bottom? Yeah, it's Kelvin. So in order to multiply temperature times entropy and have those units cancel, we need to take this to Kelvin. And remember that is just 273 plus temperature Celsius. The temperature Kelvin is going to be 290. That's what we plug in here. 298 Kelvin. And then lastly, we would plug in our entropy change. But let's take a look right here. That value is in joules. In the next step, we're going to be adding this value and that one. In order to add two numbers together, they have to have the identical units. I don't really care if you change the units here to kilojoules and kilojoules. I don't really care if you change the units to joules and joules, but the units do have to match. Often I go to kilojoules just because it tends to be smaller numbers, decimal numbers, and I like that better. If you were to go to joules, you would just see values get up into like the 10,000s. So whichever one you're more comfortable with, decimals or 10,000s, that's what you should choose. But I'm going to go ahead and convert this into kilojoules, so that's just dividing by 1,000. So 142.2 joules per Kelvin is the same thing as 0.1422 kilojoules over Kelvin. Okay. So a couple of just little nuances there with the units, but it's something that we want to make sure we keep an eye on. So now as we clean up this equation, I have Kelvin on top, Kelvin on the bottom. Those units cancel. So let me just clean this up. We've got 95.7 kilojoules minus, I'm going to multiply these together, so 298 times 0.1422. And this is going to be 42.4 kilojoules. So this is why the units had to match, because if you add and subtract, the units have to be identical. Right, so now we're just going to take 95.7 minus 42.4. And delta G for this equation is going to be a positive 53.3 kilojoules. Some things to think about. Number one, this is called Gibbs free energy. So our units spitting out in kilojoules makes sense, because that is an energy value. Now, having a positive value for Gibbs free energy, is this going to be a spontaneous process or a non-spontaneous process? Yeah, positive delta G means we'd have to put energy into this reaction to make it happen. There's nothing freely given off. It's something we'd have to add to the system. So positive value for Gibbs free energy means this is non-spontaneous. And if I look at that, it kind of makes sense. So number one, we're going from a gas to a solid. That is a lot more structure. We also have a positive change for our enthalpy, so heat has to go into the system. So we're getting more organized, we're putting heat into the system. It makes sense to me that that would be a non-spontaneous reaction. You'll see more problems like this, but just a quick introduction to how we calculate Gibbs free energy. I hope you guys found this helpful.